solving is that mx double dot plus cx dot plus kx is equals to 0. And we have seen that due to the damping, so there are three cases we have considered. One is the by defining the ratio, that is the non-dimensional parameter, that is called the damping ratio zeta, okay, which is nothing but c by cc, okay. So we have defined the three cases. One is zeta greater than 1, another is zeta equals to 1, and zeta is less than 1. So as you told, these are not our usual physical system, and most of our physical systems, especially the structural system. Hello? Is the slide visible to you, right? Slides visible to you?
Yes, sir.
Yeah, okay. Okay. So three cases you have considered, and as I mentioned already, that are especially in our structural dynamic cases. So so this is zeta is less than 1, and it is not only less than 1; it is much less than 1 actually. Okay. So in our like building, bridges, all those things. So you will find the structural system. I can confidently say that it is less than 15 or 20%. Let's say 20%. Okay. Not even 20% is too much also. Okay. It is less than 10%. For concrete structure, it is usually 5%. Steel structure, we are considering as around 2% or 3%. Okay. And for like say long span suspension bridges, right, the damping ratio is 0.5%. Okay, 0.5%. That means zeta is equals to 0.005. Okay, so you see how much less than is 180. So forget about 1. So zeta value is for this is for the long span suspension bridges. Okay, for cable stayed bridges is around 1.5%. Okay, that means 0.015. Okay. Okay. So these are the some cases, and we have discussed also some example for the overdam system and the critically damped system. This is we are calling as a critically damped system. So the motion represented by this under damped system or under critically damped system is oscillatory in nature due to the presence of the sine and cosine terms. Okay, that is the imaginary component in the solution of the characteristic equation, right? Okay, because we are finally solving the characteristic equation, right? After substituting the assumed solution in the equation of motion. Okay. And for zeta is equal to 1 and zeta greater than 1, we are getting a non-oscillatory solution with exponentially decay. Okay. And the critical damping is defined as the damping ratio for which, this is the minimum amount of damping which is required for the non-oscillatory motion of a system. Okay. Which is defined as this. Okay. Perfect. So what responses we have got so far? The expression for the response that we have got is equal to e raised to minus zeta omega nt into I think some constant c1 cosine omega dt plus c. So that we have already discussed in the last class, if you remember, right? So as I told, so this part is same as like similar to like the not same, it is similar to like the for the undamped system, except that this term, right? It was previously omega n. Now it is omega d, that is the damped transfer frequency, which is defined as the omega n minus zeta square. Okay. And omega d is less than omega n, but for you see for a very small value of zeta, which is usually in the case of the for our structural purpose, omega d is nearly equals to omega n. So I can define TD is equal to 2 pi by omega d. Like Tn equals to 2 pi by omega n, so TD equals to 2 pi by omega d. This is the damped time period basically, right? 2 pi by omega t. Okay, fine. So remember this relationship. So due to this extra term, additional term, the response are getting decayed exponentially, right? Because e raised to minus zeta omega t. Okay, depending on the values of the zeta, it is with time it is exponentially decay. That's all. That is the now. Now doing the exercise in a similar manner, we can find out the C1 and C2 as we have done for the undamped system, right? Just substitute the initial condition, that is initial displacement and velocity. We can find out the coefficients C1 and C2 and complete the expression. So please do it. So at time equal to 0, let's say my initial condition is x0 and x dot, that is the velocity. At time t equal to 0, let's say it is x dot. So substitute this here and tell me what is C1 and C2 you got. So got it right? What I asked you to do? Just find out the two constant, basically C1 and C2, by putting the two, using the two initial condition. Like the way you have done for the last time also, similar manner. So here the extra thing is there, the e raised to minus zeta omega nt, and instead of omega n inside the parenthesis, it is the omega d. Yes. So what xt we are getting? So e raised to minus zeta omega nt will be there. The C1 and C2 I want. So what is C1? So into cos omega and into cos omega dt plus something will come into sin omega dt. Yes. Please come on. What is this? What is this? Tell me. Remember that this is omega n. Okay. Zeta omega n. This is omega d. So what is C1 value you have got? The first constant. Yes. I can see only very few people.
2 into naught minus x naught dot whole divided by sine 2 omega dt.
What is C1?
C1 only. Sir.
You can see the expression that xt is e raised to minus zeta omega nt whole multiplied by C1 cosine omega dt plus C2 sin omega dt. I am asking, find out C1. This what is C1?
Sir, I'm getting C1 as x naught, sir.
Huh?
C1 as x naught.
X naught. What is C2?
Zeta omega n x naught by omega d.
Zeta
Omega n x naught by omega d. Is that correct?
by omega d.
D. Yes, sir.
No, it is not correct. What I remember, there is something else more is there. Okay. If you're getting this, then I don't know. It's fine. This again, this is very straightforward. Right? Just you substitute there, differentiate it, and then input the initial condition and just solve it. Finish. Two equation, two unknown, right? That's all. Anybody else? Is everyone getting the same? Where is the velocity gone? Where is the velocity?
God will come here.
What is the velocity? Right. So this is the x naught dot. Very surprising how the velocity would not come up. Okay, anyway, or whatever it is, just you put it and find out this constant. So now you, everything is known to you, right? So in terms of initial condition, now I can plot the responses. Okay, so if so in our normal system, so it will just exponentially decaying motion. Okay, so I'll show in the slides also. So you see this expression can again be written in this format also, that is a some amplitude into cosine of omega dt minus phi. So as we have written in the last time, so in the last time it was this much, right? A cos omega, and this was omega d instead of omega n t minus phi. Okay, so similarly here also you can find out what is the this a is amplitude, phi is the phase angle, so you can find out the values of the a and phi in a exactly in a similar fashion. So I will leave this exercise to you. So what this represents? So this represent a oscillatory motion due to this cosine term, right, with frequency not omega n. Now the frequency is omega d instead of omega n, but the important issue is that it is not only oscillatory, but its amplitude a is decaying because of this term with exponential amplitude. Okay, got it? That's done. So you can go here, you can see, so as t tends to infinity, xt becomes 0, right, because of this term, the exponential term, e raised to minus zeta omega n t. Okay, so it is exponentially decaying. As I already told, for structural system, zeta is less than 20%, even you can say let's say 10%, less than 10% also. So if you put the limit also, I mean this 0.2 also, so you are saying that the omega d, you see 0.98 of omega n, almost same, right, you can say. Okay, for the most of the engineering purposes. Okay, so now we can find out the relationship between omega d and omega n. You have already written, right? So it can be represented actually graphical. What is that graphical representation means? So this is omega d by omega n whole square. So if we take it here, the zeta square equal to 1. So what is represent? What it represent?
Equation of circle with axis wn by omega n by omega n zeta sir.
And
With
it
the
is,
radius 1.
and it is only, we are interested only in the first quadrant because all are positive, right? These are all positive quantities. Okay. So if I draw it, actually the figure is there. I don't have to draw. You see variation of omega d zeta. So if I plot zeta, that is omega d. So it is with a radius of 1, right? You see radius of 1 I have written. And you see for zeta small means what? So it is 1. So it is 20 or let's say here, right? 10% or 20%, right? So I can just see, you may find in the Chopra book, so they have hashed it or something, the color they have made. So you see it is almost same, right? So omega d by omega n is almost 1, I can say, right? So for this range. So that is graphical representation. Okay. Another interpretation, okay, of this critical damping we can say is that you see, so omega d is omega in this, right? Correct? So when zeta is equal to 1, what is omega d? What is omega d?
0.
What is td? What is td?
Sir, tending to infinity.
Infinity. Okay. What does this means? I mean the time period infinity. What is time period? Let's say this is oscillatory motion. So this cycle, this is time period, right? Td. Td infinite. That means it is non-oscillatory, right? It is not oscillatory. Okay. So that is another way of interpreting the critical damping thing. Okay. There is a non-oscillatory motion. Fine. As you can see, this figure is here. There is very already we have discussed. So undamped case, it is continue to oscillate without the any decrease in the amplitude. Then this is our undertime system. That's most of the physical system. Okay, omega t is smaller than omega n. Okay, and the others are non-oscillatory type, overdamped and the critical type. Okay, fine. That is not required for you. I'll remove it. Okay, yeah. So you see, depending upon the zeta value, right? Or basically, I can say the depending upon the roots of the characteristic equation. Remember the characteristic equation? S square plus CYM omega n square equal to 0. Am I right? This is, I think, characteristic equation, right? For the damped coagulation case. I hope this is correct. Okay. Or if it is not correct, please correct it. Okay. So the solution is S, right? S1 to everything. So depending upon the solution, right? The complex we are, I mean, in general, solution is the complex. Okay. So the system response can be like this. This is not actually stable. I should call it a just stable or merely stable. This is asymptotically stable. Okay? Most of the physical system, or ideally it should be like this. This is unstable. This is also unstable, but this is called divergent. Okay, this is exponentially growing without oscillatory motion. This is fatal instability. The last class I have talked about this, like the failure of the Tacoma-Narrows bridge or the aircraft wing failure due to fluttering. Okay. Okay, then you don't have to remember. I think just remember means I am saying that I'm trying to say that depending on the damping value or the roots of the characteristic equation, the response can be like this. Okay. Then moves to the next topic. Okay, and very important. Okay, so that is the determination of the damping. So how to find out the zeta? Okay, right? We have just known the expression C by Cc, because C you cannot find out right directly. You can find out the mass, you can find out the stiffnesses, but the C, this way you cannot find out. So you have to find out experimentally the non-dimensional parameter zeta damping ratio, and from that zeta we can obtain C. C equals to what? How to find out C? If I know zeta, what is the expression with C and zeta relation?
2m omega into
Yes, 2m omega and zeta, correct. Okay, so m you can find out, omega you can find out from root over k by m, right? So once you found out zeta from experiment, you can obtain the coefficient of viscous damping, right? So how to find out zeta? Okay, so here we introduce a term that's called logarithmic decrement. Okay, so let's see what it is. Okay, so that is actually basically represent the decay, the nature of the decay, or how fast it is decaying. Okay, and from that you will find out the values of the zeta. Okay, so what we have to do here? So you see that this is the response of an under damped system or under critically damped system. So it is decaying, okay, exponentially. So, and this is the time period Tt I have written. Tt is the 2 pi by omega t. Omega t is what? D what? Omega n root over 1 minus zeta square. Okay. So what we will do? We will just measure through experiment, right? So we will just give some initial disturbances and okay, and then we will measure the two successive peaks. Peaks is it is easy to measure, right? You can measure here also after a certain same time interval. You can measure here and here also, no problem. But a peak is the easy to measure in the experiment. Okay, so let us measure two peak time interval td, that is x1 and x2. Okay, so x1 is at, let's say, time at t equal to t1. So obviously x2 is the response at time t equal to t1 plus t2, one cycle apart, right? Correct. Okay. We'll shortly see, even if it is not one cycle apart also, let's say after 5 cycle apart we are measuring, because you see in the experiment, right, this measurement can be a little bit wrong, or there will be some issues will be there. So if I measure, let's say, for 10 cycle and then take the average, that will be better measurement, right? That's all, nothing else. No other thing is involved here. Okay, so that we will see later. First, let us do with the one cycle apart. Okay, so x1 is the amplitude of the motion, or the basically that response at time t equal to t1, and x2 is the response at time t equal to t2. Okay, now tell me what is x1. So from that expression I have written xt. Remember that xt equals to e raised to zeta omega n t a cos omega dt minus p. Go back. This one, right? Okay. So now I want to write this at time t equal to, I want to write x1. Let us call it x1. X1. Okay. That is x at time t equal to t1. Okay. And tell me what is x2. X2, right? What is that? X2. Yeah. Time at time t2. Okay. So what is the expression? Tell me. For x1 t. This one is very simple. Let zeta omega n. Instead of t, it is t1, right? A cosine omega d t1 minus. What will be the next one? Just instead of t1 it will be t2, right? Am I right or wrong?
yes, sir.
Yes. Zeta omega n. So it should be t2. What is t2? T2 is t1 plus
TD.
td. Why td? Go back. T1 plus td. One cycle apart but damped. Right? So t1 plus td a cos omega d t1 plus td minus v. Right? Use the trigonometry identity or whatever manipulation, simplification. Tell me what is the ratio. Simplify it. With the relation you already know, right? That Td is equals to 2 pi by omega t. Simplify it. Any doubt here? So what we are doing, from experiment we are finding the two successive peak responses, that is x1t and x2t. x1t is the responses at time t equals to t1. x2t is the response at time t equal to t2. Okay, and t2 and t1 are separated by a one cycle, so that is td. So it's a damped case, right? So what is td? Td is 2 pi by omega t. Omega t is nothing but omega and root over of 1 minus z square, right?
So it will come e to the power eta omega in TD.
E to the power zeta omega n td. Okay, fine. Okay, now we'll take the logarithm on the both sides, natural log. Okay, e base. So if I take it, so I'll get ln x1 by x2 zeta omega n td. So this is defined as the logarithmic decrement delta. This is called logarithmic decrement. Okay, so from if I know this, or if it's given to you, you can find out this one, right? Because zeta you can find out. Okay, so now let me simplify it, because the td is also involved zeta, right? Okay, it is not simplified yet, but I'm trying to say that this is defined as the logarithmic decrement. Okay, but till it is clear. Any calculation problem by anyone? Not understand anything? The delta is equal to zeta omega and td. We'll move further. Okay, so if it is clear, zeta omega and td. What is td? Again 2 pi by omega. 2 pi by omega n 1 minus zeta. Substitute that. So what we will get? So we'll get 2 pi zeta omega n will cancel out, root over of 1 minus zeta. So this is delta, right? So what are the unknowns here? Delta and zeta is the unknown. So if I know delta from the experiment, how will you find out delta from the experiment? Just do the experimentation, find out the two responses x1 and x2, take the natural log x1 by x2 to get delta, right? Because delta I am defined as this. Delta is basically defined as this, ln of x1 by x2. So you calculate x1 and not calculate, you measure x1 and x2, take ln x1 by x2, that is your delta. From this equation you can obtain zeta. What is the zeta from this expression? Tell me. Yes. This square, okay. Yeah, what is zeta from the expression?
So delta upon under root of 2 pi plus delta square
2 pi?
plus delta square.
Are you sure?
Yes, sir.
Everyone
So
getting this?
4 pi square, isn't it 4 pi square?
Pi square. Yeah, you have to take square, right? Then this will be 4
Yes,
pi
sir.
square.
4 pi square.
Fine. So you see delta I have obtained by experiment. So I have obtained x1, x2, take the log ratio, natural log of that ratio, got delta, put it delta here, get zeta. Okay. But as I already mentioned many times, the zeta is usually less than 1. Okay? So you can approximate it. So this actually got vanishes. Vanishes means in short, not vanishes, it becomes 1. Sorry, not vanishes. So this becomes 1. So you can further simplify. I mean, you can use this short expression also. the delta y. And in most of the cases, structural purpose, you can use this. You will get very close result as compared to this. Okay, as zeta equal to, you can use delta y. So just divide it by 2y after taking the natural log of this x1 and x2. Clear? Okay. So now, let us see if I use this expression and this expression. So how difference it is coming? You can plot it, right? As a delta versus zeta, right? You can plot it. Let's see, the plot is most probably here. Where it gone? Yes. Okay. So as I mentioned, right, measure any two displacement x1 and x2 one cycle apart. Calculate delta by taking natural log of this. Then obtain zeta from equation 18 or 19. 18, 19 will be those two equations. Okay. So you see, now I am plotting. Equation 18 is the which one? 18 is the exact one, right? And 19 is the approximate one, correct? So by plotting, you see. So what is the range of the structural damping zeta? Zeta I told is less than 20%, right? So in this range line, is there any difference? Can you see it? The difference between using equation and 18 and 19? Not much, right? And there is some difference, but it is insignificant. Right?
Yes, sir.
Very much conveniently use any either of the equation, whatever you are convenient. But you see, as the damping ratio become increased like say 60% or 0.6, then there is a substantial differences coming into the picture. As we have discussed that it is good or experimentally preferable to measure 5 cycles, 6 cycles. I mean the response after 6 cycles, so that you can take the average value or something like that. Okay. So instead of just taking the one cycle apart thing, so now let us say we have measured after j cycle. Okay, j cycle apart. So I have measured the first one, x1, and after j cycle, so there is a j plus 1, right? So that is the response is xj plus 1. Correct? The same thing, but it is not after just one cycle. Okay, j cycle apart. Okay, here. So if this is the case, is someone want to ask anything? Something? No. Okay. So if this is the case, so this is a time t1 and this is a tj plus 1, like we have done, right? So this is a t1, this is tj plus 1 at time. Okay. So now, so we are going to try to find out x1 by xj plus 1. Previously it is x1 by x2, right? We are trying to do, but this is not logarithmic decrement. I mean, ln of this is not logarithmic decrement, right? Okay. Okay. So what happened here? So I can write, so this one I can write is x1 by x2, x2 by x3, x3 by x4, so on so forth, xj by xj. Is it right? Okay. Now tell me what is this, or what is this? What is this? Yes. So this, tell me, what is each quantity represent? I can write this way, right? That is legitimate. Then
So delta, sir.
this is delta.
No, sir. Like log of that will be delta, so it will be like.
So what it will do?
It will be e per zeta into omega n 51.
Omega into ed, right? This also
Yes, sir.
same.
TD.
This also same. Dot 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 j times, right? Correct? That means e raised to,
Sir, but TD will change this.
huh? TD change? Are cycle oscillation, how TD will change? Same frequency, I mean the frequency is remaining same, right? How the frequency is remaining? Okay.
Okay, sir. Okay, sir.
Am I right here? Is it okay? Just a minute. Okay. basically j times it is. Okay. So j times you are doing it. Okay. Now, so if I take the natural log on both sides, so I can write from this delta is equal to 1 by j. So this one j will come around ln x1 by xj plus 1. Okay. Is it fine? So once you got this thing, then you can substitute this in equation 18 or 19 what is mentioned, right? So then you can easily obtain this. Okay. Okay, so we'll solve the problem after some time. Okay. Yeah. Sorry for some interruption. Okay, so this delta we have got is 1 by j ln. So you see, so let's say after 10 cycle, obtain some responses, right? So this is at the first cycle you have calculated, and after 10 cycle you have calculated xj plus 1. Okay, and x11 that is. So then you just 1 by 10 ln x1 by x11, you can obtain this delta, and the delta you put in this expression or in this expression. If your damping is very small, then you can conveniently use this expression to obtain the damping ratio. Clear? What is the time? 1:05. Okay, time is there, so I'll just discuss one more thing. Okay, now then we'll solve one problem regarding this logarithmic decrement. That will be then your all the ideas or whatever you have discussed, it will be much more clear. Okay, now as far as the energy thing is concerned, we for the undamped system, right? We have shown someone of you have calculated, right? The input energy is kinetic energy by potential energy, that is half k x naught square plus half m x naught dot square, right? Input energy. Then at any time t you have obtained that half k x t square plus half m x dot t square, and xt and x dot t, that the expression and the derivative of the expression that you obtain response expression you substitute, and after some simplification we obtain that it is same as the input energy, right? Because energy is not dissipating, there is no damping is there, but here now the damping is there. Okay, so we'll discuss more of this energy dissipation later, but just remember this expression. Okay, so energy dissipated in viscous damping. Obviously your energy is dissipated, right? That's why the response is getting goes down. Okay, dissipated in, and that is due to the damping, that's C, right? In viscous, that is Cx dot term. Okay, so you want to see, let's say from 0, for a 0 to time t1, what is the energy it is dissipating. Okay, so you have to obtain that. So if I call it Ed is the dissipated energy, so this is the damping force Fd, right? Fd is C into x dot. Okay, so it will be 0 to x, so to travel the x distance, so it will be just basically work done kind of, right? Fdt into what? Into dx, right? Right. So I can write like this, Cx dot dx. Okay, I can further write it like this, because I am to write in terms of time, right? So what we do, Cx dot dx by dt, sorry, dt. So then I can write Cx dot square, right? Dt 0 to time t1. So this is the energy dissipated in time t1 due to damping C. Okay. Now as t1 tends to infinity, obviously the dissipated energy will be tends to what? What? As t1 tends to infinity, dissipated energy will be equal to
Infinity.
energy to infinity.
0, sir.
Input energy.
Input energy, exactly, correct. Input energy, it will be input energy. Okay, so it will fully dissipate whatever you have given. So that's why the response will starting from this, then slowly going down and will finish. Okay, now solve a problem. Yes, please solve it. Try to read it 3 times. The time is there. It is only 1 9. Yeah. So you can just spend 15 minutes to do this. So I request you to everyone to please do this example. Okay, I am here to help you. There is no doubt about that. But first try by yourself. Look at them. How many quantity you have calculate? Damping ratio, that is zeta you have to find out. Natural frequency of undamped vibration, that is omega n you have to find out. Effective stiffness, that means yeah, effective stiffness means stiffness here, because we are idealizing, right, as in water tank as a single degree. That's why it is called effective stiffness. Modeled as a single degree system. Effective mass, right? Because mass are distributed, right? But we are considering that the mass is at the top of the damping coefficient, that is C, and number of cycles required for the displacement amplitude decrease to 0.5 centimeter. Okay, that means you have to find out basically the J value, and what is the number of cycles so that it's go down to 0.5 from 5, right? 5 to 0.5. So I am just reading the question again. If your evaporation case is conducted on an empty elevated water tank, okay, a cable attached, not a single layer film system, the cable attached to the tank applies a lateral or horizontal force of 73 kilonewton. So that means I am pulling it by a 73 kilonewton force and then just leaving it. Okay. So the tank moves horizontally by 5 centimeter. Got it? So from here you can find out some quantity. Understood? So I am just giving a force. I got a displacement. Okay. Static displacement. This is static displacement. Okay. And that will be like an initial condition displacement. The cable is suddenly cut and the resulting vibration is recorded. Okay. And then it is saying that after 4 cycles, that is J is 4, the time is 2 seconds and the amplitude is 2.5 centimeter. So that means you understood, right? To complete 4 cycles, it requires 2 seconds. Okay. And after 4 cycles, it becomes 2.5. Initially it was how much? 5, right? Because I have given the initial amplitude of 5 centimeter, leave it after 4 cycle, that means after a time of 2 seconds, it comes to 2.5 centimeter. So as I already mentioned, right, and I am again repeatedly saying that please look into the example solved in the book, solved example in the books. You can see all the books, no problem. Just go through the examples, okay? Just go through the examples in all the books that I have mentioned. 5 books or 4 books I mentioned. You can refer to some other books also, there is no issue. Okay, for the solving the problem. And just see how they have solved it. Okay, try to solve it by first yourself, then see the how they have solved it. Because you see, it is very difficult to solve many problems in the class during class, right? So this one problem will take 15 minutes. Okay? So out of 50-minute class, so if I spend 15 minutes in just one example, then I'll not be able to discuss about the theory. And in that case, I might go hurriedly, right, to finish the topic, and that is not a good option for you. And also be careful in the unit, right? Okay. So this you might have done already, right? What is the answer for this? B. Natural period of unnamed vibration. What is the answer for B?
0.5
What? 0.5. 0.5?
seconds.
So once you got this, you can easily find out. What you can easily find out? You can find out M. MK you can find out, right? K so you can find out very easily. So what is the C and D? That is effective stiffness and mass. First you have to find out actually effective stiffness. Anybody? What is stiffness?
So
What is the value?
1.46 into 10 power 6, sir.
1.46 into
10 power 6 Newton per
what is
meter.
the
Newton per meter.
what is the value of D? Effective mass. Yeah, just put the calculator and obtain, because you have obtained already K, right? K you obtained, Tn you have obtained. It's very simple. That Tn means omega you have got. Omega in divided by K by N. So N you know just K by N. So I request again, everybody please do it and don't take it lightly that you'll be able to do it. These are very simple problem. Okay. And if I am unable to do it also, please practice more. Okay. Or if there is any doubt or any problem you are facing, you can contact me also. Okay. Yeah. So what is the mass? Come on. What is the mass? What is the mass? Because you obtain time period, you obtain stiffness. Then the mass is just in one calculator button press. Just tell me.
So 9.24 kilonewton.
Just tell me in kg. Because omega root over k by n, I mean, right? So k is in Newton per meter and m in kg. Okay. Yes. Yeah, tell me, what is the effective mass? Anybody else? Okay, what is the damping ratio you are able to obtain? Damping ratio? Yes? Please speak out, let it be.
0368.
What?
0.0368.
0.036.
368. Yes, sir.
Any other people getting the same result of all the problem I am talking about? So what is D effective mass? Come on, someone is telling the mass, then he has just vanished. What is the mass? I think he's telling in Newton or kilonewton or something. I asked him to make it kg. What is the mass? Come on, this is time period you got, k you got. What is the problem in getting the mass, right?
So one doubt, sir.
Yeah.
Sir,
So like
0.5
shouldn't be
seconds.
like natural period of damped vibration.
Yes, sir. 0.5 seconds is natural period of damped vibration.
Damped vibration, isn't it? Like damped vibration.
No, I have not talked about any answer. Just tell me what is that? You find out now. I am not saying this is correct or anything. Just tell me what is D.
So we'll solve and give the answers tomorrow's class.
Huh? Is there any difficulty in finding the first one? A.
No, sir.
Damping ratio? Yes. Is there any difficulty in finding A? I mean the first one, damping ratio. So all the people got 0.036, right? That means 3.6% basically. You usually write in the percentage. You see, if you do not do it, I cannot help. Okay. But, well, the time will be over, already over. It is 1:24. I'll just leave it after some time. Okay. So I'll be here for 5 more minutes. So please, tell something. Okay. Because if there is no communication, then I cannot. So is everybody getting the damping ratio 0.036 or not? That is my question. What about other people? I think 1 by only 12, it is 0.036. What about other people?
So it's coming 0.02759.
0.027,
59.
that is 6.
Sir, J value we should take 3 or 4, sir. Because in
Really,
formula we derive it as x plus xj plus 1. For xj plus 1 we took 1 by j. So it should be 3, no, sir, J value.
no, it is not. After J cycle, right? First 1 and then J plus 1. That is a J after J cycle. So it is at the end of 4 cycle. End of 4 cycle.
Sir, the 2.5 is x5, value of x5. Correct, sir?
Yeah.
Okay, sir.
Okay, so 1 for ln 5 by 2.5. Okay. That is the delta logarithmic decrement. Then you can use any one of the equation to get something. So first equation you got, that is 2.76%, right? Okay. Got it?
Sir, wait, it is coming too much big, like 1.6 into 10 to the power 6.
That is the not damping ratio.
No, wait, effective mass of tower.
That can be, I don't know that. But he said damping ratio is 1.10 raised to 6. Okay. So
No,
anyway, I hope
sir,
this
I'm talking about effective mass, D part.
coming to that. So this 2.76 we have got, right? So now this is your
Yes,
damp, someone is telling this 0.5 is damp time period or something, right? Okay.
yes, sir.
Right or not?
Yes, sir, it's 0.5 only.
0.5. So then zeta you got, you can find out omega n or not? Hello, where he is gone? That is true. Omega n, omega d equals to omega n root over 1 minus zeta square. Zeta is 2.76%, right? Put it there, you will get omega n. Okay. Then effective stiffness I will find K equals to that force. Force we applied, that is 73 kilonewton divided by the static displacement. That is the 5 centimeter. Okay. So you use unit properly, you will get the stiffness. Now stiffness you know. You got the time period right, omega n you got. Can you find out effective mass? Now then the calculation you have to do, boss. Now you got zeta. Now C equals to 2m omega n zeta. M you got, zeta you got, omega n got. So you can find out C, right? Then use the similar approach to find out this F. F is how to find out F. That is what, how many cycle is required to get that your the displacement to 0.5, right? So let's say 1 by n cycle is equals 1 by, so zeta is equals to what? Zeta equals to 1 by 2 pi n, right? Approximately if I say, and ln that will be 5 by 0.5 is equals. This is 5 by 0.5, whatever unit it doesn't matter because you will cancel out same unit if it is. So 1 by 2 pi n zeta you are obtained, you can find out n. That's all. Any doubt here? Is it clear to everyone? Please do
Yes,
the
sir.
calculation. So I am again repeating last time. So damping ratio you will be able to find out, right? So you find out the logarithmic decrement as 1 by number of cycles, that is 1 by 4 here into ln natural logarithm of 5 centimeters is the starting and now it is 2.5. So 5 by 2.5. So from that you can find out delta. Now you can find out zeta as delta by 2 pi or the correct expression to get the what is zeta, damping ratio, right? So now once you got zeta, now this is the natural period of vibration, that means omega n. So omega d is we know omega n root over 1 minus zeta square, right? Zeta you obtain, but omega 1, omega n, omega d you have to find out. So omega d is the damped thing, right? It is saying that how many cycle and how many time it takes that you can find out to get one cycle, right? So from that you will get omega n. Omega n you know, right? I mean Tn, sorry, Tn you know, so that means omega n also you know. So and effective stiffness you will find out that 73 kilonewton divided by the static displacement, that is 5 centimeter. Okay. From that you will find out the stiffness. Once you got stiffness and natural frequency, then you can find out the effective mass, right? Because omega n equals to over k by m. Okay. So only unknown is m. Then damping coefficient C equals to 2m omega n zeta. M you now already known, zeta is known, and omega n is known. Substitute that you will find C. Okay. Okay. And then you can find out last one, that is the number of cycles required for the displacement amplitude to decrease to 0.5 centimeter. So you know this formula, right? Zeta equals to 1 by 2 pi n. N means here I am j, instead of j I am calling it n. ln, that is 5 is the starting, 0.5 it is asking to decrease to 0.5. So 5 divided by 0.5 ln, and 1 by 2 pi n is the zeta, because logarithmic decrement is zeta is logarithmic decrement delta by 2 pi, right? So that is what I am written. You can find everything is known here, right? Zeta you know, you have to find out n. Okay. So now tell me what is n you have got. So what is this number of cycle? What is the number of cycle? What is the number of cycle? Come on. What's the number of cycle? Everything I have written here, right? What I have written? I have written zeta is equals to,
approximately 14, sir.
yeah, that's all. 13 or 14, right? 13 or 14 cycle.
13.57, so it's I think 14.
14 you can write, yeah, no problem. You see, these are the answers I have written. This might be approximated, but it is closer to the correct one. You can see. So I am just removing this here. So zeta is 2.75%. Tn I have written 0.5 because the damping is very small, right? So 2.75%. What is the difference between Tn and Td? Can you tell me? So that's why I have written 0.5. Okay. And K is this, M is this, C is this. You might get something around like this in a 13 cycle. Okay. That's all. So thank you all. We will meet in the next class in the next week. Okay. And so basically our first part is over. So that is the free vibration, undamped system and damped system. Now we move to the force vibration. And first forcing function will be our harmonic forcing function. We will see some more interesting things to come. Okay. That's all. Okay. Thank you all.
Thank you, sir.